Okay, so let's start from maybe here, right? So we were discussing that in any machine learning, what is the final output? The final output is a mathematical equation. Okay. Now, if it is a mathematical equation like this, for example, right? The one limitation is we cannot have categorical variables because we cannot say one time male or zero time female, something like that, right? So because on categorical variable there cannot be any mathematical operations that we can do. One of the thing that we need to do before starting machine learning in our data set is to convert our categorical variable into numeric. Okay, so for example, if I have a male female gender flag, right, which is having values like whether someone is male or female, what we are going to do is we are going to create, let's say, two flags. One is male flag, one is female flag. So male flag is whenever the customer is male, then it will be one, otherwise it will be zero. Whenever the customer is female, it will be zero, otherwise it will be one. Okay, so this is our male female flag. Now, our machine learning models are smart, right? They are not dumb. So if you will feed anything unnecessary into it, right? It's then that thing will not be useful. It's not like that if you will feed both the data into the machine learning model, it will get confused or it will give you wrong results. No, not like that, right? It will still give you the right result, but the computation will unnecessarily increase. Or I would say your run time, the model training time will increase, the model equation will become more complex. So we try to reduce as much variables as possible. So here we can obviously see that male flag and female flag both are not required. Any one of these two will work. If you will give me male flag, that is also fine. If you will give me female flag, that is also fine. But only one is enough, because if you will give me one, I can tell you the value of the other. Similarly, here in the age group column, we can see that there are three distinct values here: 0 to 10, 10 to 20, and 20 to 100. Okay. Now, here I can create three flags out of it. One is a flag for 0 to 10, one is a flag for 10 to 20, and another is a flag for 20 to 100. Okay. Now, we don't need all the three flags. If you will give me the value of any two flags, that will be enough. Okay, and I can predict the value of third on my own. So again, any two flags you need to choose, and the third one you will drop it, right? So the number of columns will always be equal to n minus 1, where n is the number of categories. So if you have 5 categories, I will have 4 columns. If you will have 10 categories, I will have 9 columns. If you have 20 categories, I will have 19 columns. Okay. Then we were discussing this part. Let's say if I want to predict the height of a human being and you have not given me anything about that person, then my prediction is going to be the average height, right? That is 155. So for anyone whom I don't have any data about, there my prediction is going to be the average height, that is 155 in this case. Now, if I will tell you that I know the gender of the person, that is, I know that whether he is male or female, then my prediction will improve. Okay. Now what I will say is, for male it is 160, for female it is 150. And how the equation will change? Earlier the equation was simple: y is equal to 155. Now the equation is y is equal to 150 plus 10 time flag, where 10 is nothing but your male flag. If you have decided to convert this gender column into a numeric one, and you are keeping only male flag, then this is how the equation will look like. And prediction will be, if you solve this equation, for male 160, for female 150. And if I will decide to keep a female flag instead of male flag, then my equation will look something like this, right? And the output will again be male equal to 160, female equal to 150. So point being is, depending upon which dummy variable you have chosen, okay, your equation might change, but your prediction will not change, right? It's not like that if you choose male flag, then your model will be more accurate as compared to if you choose female flag. Okay, irrespective of whether you use a male flag or female flag, you will get the same accuracy. Okay, it's just that the equation will change. Moving on to the next part. Now here, I had one more variable. So we are saying that we are not limited to knowing only the gender of the person. Now let's say we know the age of the person as well, right? So what my prediction will look like? The prediction will look like this. If a person who is male, who is 0 to 10, this is the average height that I have for this particular group. So my prediction is going to be 130 centimeter for anyone who is male and between 0 to 10 age, right? And from an equation perspective, this is how the equation will look like. Okay, so see, we have just added two variables, age and gender, and the equation is already getting complex, right? The previous equation I could have written on my own, but this equation, to be very frank, was a little tough to write on my own. Now just imagine if I will add a lot many other variables, right? If I will add, the ethnicity of the person, the parents' height, how good of the diet that person has in his life, and all of these things, right? Then the equation will become much more complex and it will be very difficult to do just using your hand, right? Without taking the help of machine learning. So yeah, this is how in general machine learning works. It just nothing but it tries to come up with an equation which can predict all the values. Let's say, for example, in this case, this equation can predict all of these six values. Right? Now,
What are the
mhm,
six values? Can you show?
these are six values: 130, 150. This.
Like what it is predicting, what is 130, 150, these are heights.
This is height. Yes.
We already have height, right?
No, no. This is for a person. Let's say of whose height you don't know. Okay.
Oh,
Let's say here I know. Obviously, if you'll ask me for customer one, 168, for customer two, 155. Let's say there is a new customer, right? In the future, you don't know the height of that person. You're supposed to predict it. Okay. So on this data we have trained. Now, whenever there's a new customer who's coming, what we are doing is we will just see what is his gender. Let's say he's male. What is his age? Let's say he is 22 years old. So I know that he will fall into this bucket. So my prediction for his height will be 170 centimeter. Okay.
okay. For both male and female, the equation is same.
Yeah, right. For both male, female, for all the genders, the equation is exactly the same. If you will impute the value in this equation, you will get the prediction for that particular person. Let's say I said he's a male and he's 22 years old. So what I will do is 120 plus 10 times gender, 10 into 1 because he's a male, plus 20 times into 0, right? Because he is not from 10 to 20, plus 40 times into 1. Why 1? Because he is from 20 to 100. He is 22 years old. So it will become 120 plus 10 plus 0 plus 40. That is, yeah, 170
180.
centimeters. 170. 120 plus 110 plus 40. 170 centimeter. Okay. Which is same as, let's say, what we have over here.
Like how we know how to write the equation?
We need not to write it, right? The
Okay.
thing is that, as I was telling you, right, maybe if I will give you this task to kind of write this equation, maybe after certain permutation combination, you might be able to write this equation on your own. But if I will add more number of variables, right? If I will add 10, 20 more variables, you will not be able to write it. Right? And that's why we have machine learning. This equation is nothing but the output of a machine learning model. Okay.
Oh, okay, got it.
Now, so we have discussed already one problem where we said that, if the values are categorical, we cannot use them because in equation, a mathematical equation, I cannot have a categorical column. Similarly, if I have missing values, that is also a problem, right? So for missing value, we discussed that, okay, in general, this is the rule that you can follow. 0% to 2%, you can remove the rows. 2% to 20%, you can impute the values, right? Or you can replace the value with mean, median, mode. And for greater than 20%, in general, we drop the variable itself. Okay. So yeah, this is what we have discussed so far. Now, okay.
Can you
Yeah.
explain about this variable part? Like I was absent the last class.
Which missing value treatment part?
Where variable this one, yeah.
So it's just simple that if you have missing values somewhere, let's say in a particular column, there can be certain values which are missing. If your 0% to 2% of the rows are missing, then you can remove the rows altogether. Okay, because it's not worth figuring out what should I replace it with XYZ, right? If it is very small percentage of rows, just remove it and use that data. But let's say if 2% to 20% of your rows are missing in a particular column, then I cannot remove the rows. I cannot remove 15% of my data, 18% of my data, like 5% of my data. So in that case, the only option that you have is to impute the values, right? To replace the missing values with mean, median, or mode. And the last one is like when your variable have more than 20% missing values, let's say your variable has 30% missing values. In that case, you should not impute the values. Okay, because you cannot replace 30% of the values based on 70% of the values, right? So in that case, it's better not to use the variable altogether. That's what I mean by dropping the variable.
Okay.
Now, so we have discussed about that. Okay, if the categorical column is there, what needs to be done? If missing value is there, then what needs to be done? Another part is, let's say now you have your data ready. Okay, hypothetically, let's say you have now your data ready. What will you um, do next? Okay, let's discuss that. Okay, now once you have your data ready, in general, the very first step that you will do is you will split the data into test and control. Okay, let's say this is what your whole data set is. Let's say this is what my whole data set is. I will split this data into two parts. We call it test and control. My bad. Test and train. Okay. Training data and testing data. Testing data is in general kept at 20%. Okay, so you randomly select 20% of the rows and you remove that data and you call it as a test data. And the remaining 80%, is called training data, right? What is the meaning of this? So let's say, you are a teacher, okay? And you are teaching a student. Now, if I have for practice, I have 10 questions in hand. Okay, if I have 10 questions in hand, what I will do is I will use 8 questions, right? To kind of discuss the concept or to explain the concept in the class, right? And then to check whether the students now have understood the concept or not, what I will be doing is I will be taking another 2 questions, right? And I will be asking these questions to the students, right? Make sense? This is how we do in general whenever we want to teach a student, right? The same thing is happening in case of machine learning as well. So what do we do? Okay, what we do is, let's say, I have my data, right? I will divide them into test and train, okay, which is nothing but 80% of the data. On this training data set, I will be exposing this data to the machine learning model. Okay, you need to expose this data to the ML model. Okay, now the ML model will learn based on this. Okay, the ML model will learn based on this. And once the model is learned, okay, now when you feel that the model is ready, it has learned the pattern, then what I will be doing is, once this is done, I will test my model on unseen data. Okay, unseen data is nothing but your test data. This is something that your model has not seen before. So I want to see, let's say, if I will ask my model a question which it has not seen before, what is going to be the performance of the model on that particular data set, right? Because that is the true accuracy of the model. Because obviously the data that I have used to train my model for prediction, I will not be using the same model. In the future, there will be a different data set which will be coming. So I want to see that in future, when there will be unseen data which will be coming, whether my model is being able to predict those data points correctly or not. Okay, so for any model, we conduct 2 kinds of exam. Any model will have 2 types of accuracy: training accuracy and another one is test accuracy. Okay, so any model will have 2 kinds of accuracy: training accuracy and test accuracy. Training accuracy is nothing but how my model is performing on the seen data, right? The data which was used for training the model. And test accuracy is nothing but how my model is performing on the unseen data, right? Or you can also take it as, like, this is how I try to remember it, that this is more like a class test, right? In a class, a teacher is training the student, okay? He will be taking, let's say, a lot of examples in the class. And then from those examples only, he will be asking you question to check whether you have understood correctly or not. Okay. And similarly, once, let's say, we feel that the student is ready, we will be conducting the board exam. What is this board exam? In board exam, there will be questions coming which the teacher might not have covered in the class also, right? But the concept is covered, right? But the exact question might not be covered. The same is there with training accuracy and test accuracy. Okay, now there can be multiple scenarios from here. Let's say I have um, 3 students. I have 3 students. Let's say student A, right? Student A is there. And what student A does is, right, whatever is covered in the class, right, whatever you're going to cover in the class, right, she will mug up everything, she or he. Okay. So this student is going to mug up everything which is going to cover in the class. Okay. Then student B is there. This student will try to learn the concept behind the question. Okay. And then there is student C. Right? Who will always be on mobile. Right? So let's say in any class you will find these 3 kind of students, right? One is student A, right? He or she doesn't care about the concept. Whatever is covered in the class, like they're gonna mug up everything. Then the student B is there who is trying to learn the concept that, okay, why the teacher is saying this, right? And then student C is there who is not giving attention in the class and always on the mobile. These things are happening. Now, for these 3 students, right? If for these students, if I will ask you, who will perform how in a class test?
Student A will perform better.
Student B will perform better. I think student A will not, means if we are given the questions out of the box, like in board exam, then he is going to fail. Student C will fail in even class test and board test.
Okay.
Class test A, board exam B.
Right. Very nice. Right. So let's say if I'll make a guess, it might look something like this. Let's say for example, in the class test, it might happen that the student A has scored, let's say, 98% marks. Okay. The student B might have scored a little less, let's say 92%. And student C, because he or she is not attentive in the class, they might score, let's say, 50%. Right? These, when I say class test, these are the questions which are already covered in the class. Right? So that's why the student A is being able to perform very good in those on those questions. Now, let's say if there is a board exam and now the concept is going to remain the same, but the questions might change. Right? Now what will happen? This the student A might score only, let's say, 70%. Right? This student here, there will also be slight drop for her, let's say 89%. And let's say for the student C, because she was anyway not attentive, let's say 47%. Right? So even in the models, you will see these three kind of scenarios, right? Can the fourth kind of scenario is also possible? Let's say student 4. Let's say student D is there. Uh, he is also same as student C. It's just that, he got maybe 50% here, but got 90% here. Is this scenario possible?
Yes, it can happen if it cheats.
Yeah, if he cheats, right? But unfortunately, for a machine learning model, that is not an opportunity, right? So I agree with you, right? In real life, maybe possible, but when it comes to machine learning model, it is not possible that it is not being able to perform good in the class test, but on the training data, but being able to perform very good on the test data. In general, this never happens. If it will happen, it will just be by chance, right? It is not any concept, it is just by chance that it is happening. Just 1 minute, it's not responsive. Okay, so the fourth scenario is not possible. Only the first three scenarios are possible when we are building the machine learning model. And which is the best case scenario according to you? Is it
And B.
the B is the best case scenario, right? And if I will ask you, like this is not possible. Why it is? Okay, so this is not possible. But for the other three scenarios, obviously those scenarios are possible. Mhm. Okay, let me close and reopen this. Let me close and reopen this. That was not responding. Right. So obviously, when we will look at from a machine learning model perspective, it is not class test or board exam and all. The term that we use is training data and test data. We call this one as training data or our train accuracy. And this is what we call it as our test accuracy, right? How the model is performing on the training data, how the model is performing on the test data, okay? Or unseen data versus seen data, right? Now, all of these scenarios have a different name in machine learning, okay? When I have a model which is performing very good on the training data, but not so good on the test data, it is called overfitting.
Overfitting.
Yeah. Okay, we call it overfitting. In this scenario, this is where we have good accuracy on, on both the side. We call it best fit model. And for this one, right, we call it underfit model. Right, and we have no name for the last one because that we assume will not happen ever. Right, and if it will happen, it will just be happening by chance. Okay, now in all these cases, what is my model accuracy? Okay, if I will ask you here in this case, what is my model accuracy? In the first case, is it the average of these two
Train,
or?
train accuracy maybe 90 to 100%, but test will be in 40 to 50 or 60%. For student, means in the second scenario, it will be under like 90 to 95%, the best fit, or
No, no,
98%.
no, 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 no. Let's say, for example, this data is given to you. I'm giving you this data, and then I'm asking you, what is your model accuracy?
No, ideally, the accuracy of the model should be decided on the basis of the data on which we are testing the model. The test 70, 89, and 47 should be the accuracy of the model.
Right, very nice, right? That's correct. So if I will ask what is my model accuracy, right? Model accuracy is not the average of these two, not training data accuracy. Model accuracy as simple as the accuracy on our unseen data, that is our test data. So here in this case, the model accuracy is 70%. Here the model accuracy is 89%. Here the model accuracy is 47%. Okay, so this is what our model accuracy is. If you have this data, we can tell what is the model accuracy. The accuracy on the unseen data is called the model accuracy. So which is the most accurate model here, right? The model B.
Student B.
What is the definition of underfit?
Underfit means that on both training data and test data, the model is not being able to perform good.
Okay.
Okay, and overfitting means that the model is being able to perform good on the seen data, but not on the unseen data. Okay. Now, one question can be why these scenarios will happen. To be very frank, whenever I want to imagine it, I always imagine it as a teacher and a student. Like whatever the reasons that are possible in a class, the same reasons are possible in building a machine learning model as well. Okay. For example, when you are overfitting, right, it means that you are being able to perform good in the class, but not being able to perform so much well on the unseen data set, right? Sometimes the main reason behind that is that you don't have enough data, right? Let's say you were, just imagine when you were a child. If I will tell you, beta, 2 plus 2 is 4, 3 plus 9 is 12. Beta, tell me what is, 13 plus 11 is, right? If you are seeing addition for the first time, and if I will give you two examples, will you be able to tell me what 11 plus 13 is?
No, it will be difficult, I think.
Right, it will be difficult to tell. Right? But at the same time, let's say you are a bright student. If I will ask you 2 plus 2 is 4 beta, 9 plus 3 is 12. What is 3 plus 9? Tell me what I told you. You might be able to tell me that it is 12. You got my point. So when there is, let's say you have chosen the right model, okay, but when you do not have enough data to train on, in that case, sometimes we see the problem of overfitting. Because the model is not being able to learn enough. You have not given enough example right? That so that the student can learn. And that is the case when you say we have the problem of overfitting. Okay, underfit, when can it happens? Let's say when I'm, let's say, trying to teach integration to a class 3 student. What is the meaning of that? That the problem is very complex, but you are using a very simple model. Okay, the model itself is not capable enough to learn those complex patterns, but you are still using that model. So irrespective of how much data I will feed into that model will not be able to learn. To a class 3 student, I will not be able to teach him integration irrespective of how many examples I'm going to take. He will not become expert in integration. Right? So underfit happens a lot many times when the data, the pattern is complex, but you are using a very simple model to kind of predict that. Okay, now another question. Let's say, I'm working on some model, right? You don't know what the data set is, what you don't know what is the problem statement. All you know is that I was working on a data set and my training data accuracy came out to be, let's say, 80%. And my test data accuracy came out to be, let's say, 77%. Right? And let's say, someone from you, let's say Akshay. Okay. So Akshay is also working on a problem statement. Again, some different problem statement. I don't know. I don't know the data. He is just working on some problem statement, and his training data accuracy is let's say 60%, and his test data accuracy is 57%. Now, if I will ask you, right, the accuracies that the Puneet is getting, right, is it the best fit model? Is it uh, the overfit model, or is it the underfit model? What kind of model it is according to you?
Depends upon the complexity of the problem statement and how accurate we want the model to be.
We always want our model to be as much
As
accurate.
accurate, yeah.
Yeah, right.
So also it depends upon the how much data we have fed to the model. So comparatively to Akshay's model, obviously it is better.
Akshay's model is better
No,
compared to
no,
him.
compared to Akshay's model.
Acha,
Your model is
compared to
better.
Akshay.
Yeah,
Okay.
yeah.
Okay.
So
Okay, let me ask this question this way. Can this be a case? Can this be a case that this is the underfit model,
no,
No, I think it's
right?
no,
best fit.
And this is maybe best fit model.
could be.
In which scenario it will be possible?
No, Akshay's model can't be best fit model. The accuracy is too low.
Okay. Okay, let me tell you this. Akshay's model is actually a best fit model, and Puneet's model is actually an underfit model.
Okay.
Tell me in which scenario it will happen. Okay. Now I've given you the answer. Right?
Okay.
It can be two different problem statement, can be two different data set, but all I know is Puneet's accuracy of training and test data is this much. Akshay's accuracy is this much. And I'm telling you that Puneet's results are underfit and Akshay's results are best fit. In which scenario this will happen?
In Puneet's scenario, it would be underfit under the conditions if the complexity of the model is too simple and we have fed enough data to the model. Still, it is not giving the accurate answers to us. Whereas in Akshay's case, it is the opposite. So
Mhm.
complex, it is a very complex model. We don't require the model to be very accurate,
Mhm.
but still in cases it is giving us the accurate answers. So it is the best fit under those scenarios.
What I think is Puneet's data will be on a very limited where it is having underfit. Akshay's might be having a large data set.
For Akshay, there
Might.
might be a consistency between the trained data and the test data we are providing,
Mhm.
which also implies that the model basically generalizes that what kind of fit can be done. But in this case,
Mhm.
since the data is consistent between train and test data, so it might be the best fit. And for the Puneet model, since you
Mhm.
don't know what is the accuracy level and they are moderate, they are not even consistent. So they,
Mhm.
they might not capture the exact complexity of the problem.
Mhm.
So that's the reason it is an underfit model.
Got it. Right. So yeah, I think you guys more or less covered, the points that I wanted to make. The first thing is obviously it depends upon what kind of a problem statement it is. If I'm trying to differentiate between, let's say there are two images, right? A data set is there, which I want to tag whether it is mm, whether it is a elephant or whether it is an ant. Okay. I and If I will show you an image, with how much accuracy can you differentiate whether it is an ant or whether it is an elephant?
100%.
With 100% accuracy,
Yeah.
right? And obviously, if it will come to the machine learning model, you always want the machine learning model to have a higher accuracy than a human being can achieve,
Yeah.
right? So a human being, let's say if he's being able to achieve 100% accuracy, or let's say in worst case scenario, like 98, 99% accuracy, I am assuming that a computer or a machine learning model should be able to achieve a better accuracy than that, or at least the same accuracy if it is being fast, right? A model which is not fast, not accurate is a useless model, to be very frank, right? Now, in this case, when I want to differentiate between an elephant and an ant, it is a very simple problem. A machine learning model should have accuracy close to what? Close to 100%. Now, if the model is giving me 80% accuracy, is it a good model? The answer is no.
No.
Okay, it is not a good model. Right. Similarly, let's say if I want to predict the stock market, let's say whether a stock price will go up or whether it will go down. Okay, I want to check that. Now, in that case, if there is someone who is being able to develop a model which is 60% accurate, right? Is that a good model? The answer is yes. Okay. In case of, let's say, stock market, a model which can predict with 60%, 65% accuracy is considered very good model, right? So Akshay's model, if he's working on the stock market data, will be considered as the best fit model. Similarly, Puneet's model, if he is trying to differentiate between, let's say, elephant and an ant, right, with the 80% accuracy, is going to be considered as a bad model. Okay, so our definition of underfit and best fit depends a lot on what we are trying to do. Okay, if the problem statement is complex, even a low accuracy can be considered as best fit. If the problem statement is very simple, even a very high accuracy can be considered as underfit. Okay. In general, the overfitting case is easy to identify. Okay. Easy, because in overfitting, all we are looking at is the difference in training and test data accuracy. If the difference is significant, you can call it overfit. If the difference is not significant, you can call it best fit. Okay. Now let me ask you another question.
So for your last statement, I mean, can you go back to previous slide? One more,
One
20th
more.
slide.
Okay.
So you said, like, difference between these two, if it is significant less. That is best fit, then overfit, underfit.
Right.
How about the percentage? It's like 70% and 77%, or with the lesser numbers. Like, how do we interpret those results?
Let's say one is 70, training data accuracy is 70%,
Yeah,
and test data is,
around 77%.
that will not happen. No? In general, test data accuracy will not be significantly more than trained data. Right? This
Okay,
scenario was saying,
let's say the other way around. I mean,
okay.
77 and 70. Yeah.
Right. So 77 and 70, see, there is no a cutoff for, there is no cutoff way above which I will be start calling that this is now not overfitting and this is the best fit model. Let me try to explain it using an example. Okay.
Yeah, yeah.
So let's say Aman is creating one model and Rushal is creating one model. Okay, these two guys are creating a model. They're working on the same data set, same problem statement. Now, Aman has created, let's say, model and his training data accuracy and test data accuracy I'm giving you. The training data accuracy for Aman is maybe 80% and test data accuracy for Aman is, let's say, 78%. For Rushali, the training data accuracy is maybe 95% and test data accuracy is, let's say, maybe 83%. Okay, let's say this scenario is there. If I would have to choose one model between, let's say, Aman's model and Rushali's model, which model will you prefer?
Aman's.
Aman.
Aman's?
Yeah.
Why? Why?
The accuracy between the test and training model is not very significant. The difference. So it is more, yeah, that's the main reason.
Any other thoughts, anyway?
In the second case, my testing model is giving more accuracy than the first case. So I would prefer the second one. And the 95% train means it is more accurate on the training model. And while testing it, it is giving more accuracy than the first model.
I mean, are they working on a same problem statement?
Right. Same problem statement, same data set.
Oh,
in addition to looking the difference, we should also do we need to look at the the training and the testing accuracy as well?
Not much, right? To be frank, let's say, for example, in this case, right, if I was you, I would have chosen this particular model. Why? The reason behind that is, as you guys have already said, here the model accuracy is 78%. And here my model accuracy is 83%. Okay, so this model is definitely better as compared to this model, right? But this difference that you have between training data and test data, right? Training data accuracy is 95%, test data accuracy is 83%, right? Again, think it from a student's perspective. If a student is being able to perform very good, let's say in a class test, he is being able to perform like score 95%. In a test, in a board exam, he's getting 83%. Don't you think that with more training, it is possible that we can increase the test data score as well?
yeah.
Right? Just like a student, if I
Yeah.
know that someone is being able to perform good in the class test, but is not being able to perform in that much good in the board exam, right? Maybe if I will train him a little harder, right? If I will share more examples, if I'll explain the concept again, maybe his board exam scores will also improve, right? But let's say if we'll talk about, let's say, Aman's case. In this case, what is happening? He is not being able to perform that much good, even in the class test, if I'll compare it with the Rushal. All right. So there is not much scope of improvement also. Right. Even if I will work hard here, I would have to work hard from both the perspective that, okay, he is not being able to understand the concept well. So it means that I need to work like almost twice as hard so that he can start performing better, both in the class test also and in the board exam. But when it comes to Roshali's case, right, she is already performing better in the board exam as compared to Aman. Right? Let's say in this scenario, right? Here, why I was choosing student B over student A was because student B at the end of the day was performing better in the board exam. That's what the main thing is. Right? So I will always be choosing student B over student A in this case. But the example that I have just taken here, Rushali, although performed very well in the class test, but she still has performed better in the board exam as compared to Aman. Okay, so I will still be choosing Rushali's model only. Right? Although, if someone will ask me, can this model be improved further? I believe yes, there is a scope of improvement that we have in Rushali's case. Okay, so we can try to improve it further. So in general, what we consider is that whatever we are getting as a training data accuracy, that can be set as a target. That if I'm being able to get, let's say, 95% there, then it means it is possible to get 95% or close to 95% in the test data also. Okay, sometimes we try to do that, we don't succeed. Right? Sometimes we try to do that and we are able to increase the test data accuracy as well. Okay? But even, let's say, if I'll take the models as it is, I will choose Rushali's model here as compared to Aman.
So, like if, for example, if there's another model, say train equal to 90%,
Okay.
okay, and the testing is around 85,
Right.
say 83%. The train is 90%, and test is also 83%, another model. So which one would be better then?
In that case, you can choose any of it. So if that is your final result, right, then you can choose any of it. Because at the end of the day, what matters is model accuracy, which is nothing but test accuracy. What was the train accuracy does not matter much, right? But if you will say that, okay, I will give you one of the model and then you can try to improve it, then I will choose the one which is having 95 training data accuracy as 95%, because there I have a scope of improvement.
Okay, got it.
Okay, but if you say no, these are the final models, you cannot tweak it further, choose one of it, then my answer will be give any. Right? If both the accuracies are exactly the same, let's say one is 84, one is 85, you can give me any model. It does not matter. See, at the end of the day, how you are going to use the model? I'm going to take the model and I'm going to predict it on unseen data. You guys agree? Right? I will take a model and I will predict it on an unseen data. This is how I'm going to use the model finally, right? So it does not matter what the training data accuracy was. Even it was 100%, it does not matter. Okay. So all that matters is what the test data accuracy was. Why training data accuracy is important for us? The training data accuracy is important for us because it tells us how the student or how the model has learned. All right. Whether there is any scope of improvement or not. Right? What is happening? Whether the model is mucking up things or whether the model is actually understanding the things. So those kind of concepts get a little clear when you look both training data and test data accuracy together. Although what matters at the end of the day is only test data accuracy. Okay. Any question?
Sir, like, we have seen the test accuracy and the training accuracy, but do we need any records as well, to validate or not required?
Records, you mean?
or we only train and test? I mean, there's no validation required whether the test is accurate or not, whether the test is correct or not.
Right, right. There is actually a concept of holdout as well, right? But not relevant. As of now, as of for today, it is not relevant. Okay.
Okay. Okay.
Uh, yeah, so this is
One question,
fine.
sir.
Yeah, tell me.
Why, yeah, test, right?
Mhm.
Why 33% and test is 70? We can use 100%, right? Testing the data.
No, no. How can you like so testing data is the unseen data, right? If you will keep all the data, like I have 10 questions in my hand, right? I'm using 8 questions to teach you and 2 questions to finally test your understanding later, right? If I will keep all the 10 questions with me for testing your understanding, how will you learn,
Okay, okay.
right?
Yeah, got it. Thank you.
Sure. So training data is nothing but the data that I'm showing you that, okay, 2 plus 2 is 4, 3 plus 7 is 10, 9 plus 10 is 19, 20 plus 20 is 40. So I will take a lot many examples like this. And then finally, I will ask you a few questions that you might not have seen before. Let's say, what is 10 plus 32? Okay, then I will see that, okay, whether you have learned addition or not. Any other question, anyone? Okay, we will discuss one more concept and then we'll move to the next topic. Okay, so on, let's say, one side, I have error rate, not accuracy, okay? Because the graph that I'm about to make is in general made with error rate rather than accuracy. So I will use the standard chart, okay? This is model complexity. One more thing, model complexity is in general correlated with number of variables. More the number of variables, more is going to be the complexity of the model. If I, let's say, try to correlate it with the example that we were discussing, like here, this was a very simple model, y is equal to 155. Then I made the model little complex, y is equal to 150 plus 10 times male flag. Then I made the model a little bit more complex, y is equal to 120 plus 10 times gender plus 20 times, let's say, age between 10 to 20 plus 40 times age between 20 to 100. So between this model and this model, which one is more complex?
The third one.
The third one, right? This one.
Yeah.
So in general, more the number of variables you will add, the more the complex the model is considered. Okay. So when I say it is a complex model, it means it has a lot of variables. Okay. So let's say here the model complexity is low. On this end, the model complexity is high. Okay. Actually, let's make it with accuracy only. Let me just think once. Okay. So obviously here the model accuracy will be low, and on this end, the model accuracy will be high. Okay. Now, whenever we will start with adding more variables, will my accuracy increase or will my accuracy decrease?
Accuracy decreases.
If you will add
Inversely
more
proportional.
More variables, more reduced in accuracy.
Okay. Let's say, so if I'll talk about here, so you are saying that my first model was more accurate than the second one?
Yeah.
My first model was more accurate than the second one. If, let's say, if you need to predict height of someone, don't you think that gender is an important information or age is an important information?
It is.
right? So why the first model will be more accurate than this one? This is a more accurate model, right?
Yes.
You guys are aligned on this, right? You are not saying yes because
But
I asked the question. Yeah.
in this model, we are introducing a variable.
No, we are not reducing variable. We are adding variable.
Yeah,
In
that's
the
what I'm saying. In
Uh-huh.
this one, there's no
Uh-huh.
variable, the first one.
Right. Yes.
In the second one, we are introducing
Introducing us. Okay. I thought you were saying reducing variables.
no,
Okay. Okay.
introducing a variable. So ultimately, it is a little more complex than the previous one.
Right. But is it a more accurate model or not?
It is accurate.
Right.
Yes,
And what
accurate.
about this case?
Yeah,
Is
it
it
is
more
more
accurate?
accurate
Yeah, it is
for the
more accurate.
variables.
Right. So if I will add more variables, my accuracy will go up or go down?
It should go up.
It should go up, right? Everyone is
Yeah.
aligned on that,
Yeah,
Yeah.
should go up.
right? So let's say I'm starting with somewhere here when the model was not that much complex. It means that there were few variables in that. And then I started adding more and more variables. Okay. The accuracy will start going up. And as you will keep adding more variable, the accuracy will go up. And this is what my train data accuracy is in general. Okay. But when it comes to your test data accuracy, right, as you will start adding more variables, it will start going up. It will be a little lower than trained data, right? It happens, right? If you look at all the examples, I have always said the test data accuracy will be a little less than trained data. Okay, so test data accuracy will be a little less. It will also increase with trained data, but after a point,
It will reduce.
if you'll add more variables, it will start going down. Okay, it will start going down. And again, these are all generic things that I'm telling you, right? That most of the time this happens. In general, I cannot make a rule that this will always happen, right? But in general, you will see that this is what is happening. Now, at which point I am getting the highest model accuracy? At this point, right? This is the highest modal accuracy which was there because my test data accuracy is considered as modal accuracy. Okay, so what I can say is almost I can say that more or less this is the region where my model is underfitting. Is that correct? Because both training
Yeah.
and test data accuracy was low.
Yeah.
Right. So this is the model. This is the region where the model was underfitting, and this is the region where the model is
Best fit.
overfit. Right.
I'm saying.
Right. This is the overfit model in this region, and here in between. Right. This is the region where the model is best fit. Okay, so always remember, when as we start adding more variables, we will see that the model accuracy is going down, and as we will, uh, you know, uh, keep adding more and more and more variable. After a certain point, the test data accuracy will start going down, but the training data accuracy will always increase as you will add more variables. Okay, so this one we have as underfit. This is best fit. And this is the region of overfit. Okay, just one thing that you guys can keep in mind, that what might be happening if you are seeing an underfit model, best fit model, or let's say overfit model. When you're seeing an underfit model, then most probably you need to add more variables, right? It is more of a like I'm trying to I'm asking you to predict height, but I'm not telling you the gender and age of that person. Irrespective of how much good of a model that you are creating, if I will not tell you what is the gender and what is the age of the person, believe me, you cannot predict accurate height with a very good accuracy. Okay, you cannot predict height with a very good accuracy if the key variables are not present. Similarly, if I will add too many variables, like in which school you went to, what was your father's height, what was your grandfather's height, what was your great grandfather's height, right? What is your mama's height, chacha's height, mosi's height? Like I will put all of these, right? Then it can happen that your test data accuracy will start going down, because now you are making model unnecessarily more complex. Okay. Cool. This much all on this. Now, what we will do is we quickly discuss, some part of mathematics, that is your differentiation and integration a little bit, and then we will move on to uh, linear regression.
I have a doubt.
Mm-hmm.
Like in this graph, why there is less difference between train and test, and as we go towards overfit, there is large difference between them.
Because that's the definition of overfit, right? In overfit, what happens? The training data accuracy is significantly higher as compared to test data accuracy. Okay, if both will move together, let's say even till the last, if train and test data are together, then the test data accuracy will also increase, right?
Yes.
Right. So then it will not be a overfit, then it will be a best fit model. We call it overfit only when the training data accuracy is high, but the test data accuracy is low.
Okay.
Like for the best fit, the accuracy is same.
Okay.
For the train and test,
Likta, your voice is not clear.
like for the best fit case, the training data and the testing will be accuracy will be similar.
Similar, yes. It will be similar and it will be high.
Like how much data how much we train, it gives that much output accuracy.
All right, yes. Right. It depends upon the data, it depends upon the problem statement as well, that what will be your accuracy. Okay.
The training data and testing data, should it be always like 80%, 20%, or it can
No,
be
we can
more?
keep it 70-30 as well. But in general, that is the two options that you have: 80-20, 70-30, max to max. I have not seen people doing 60-40 or something, 50-50. That is not the option. Right?
Is there a reason for that?
Then the training data will become too less.
Okay.
Right? When you are see, I want my testing data to be as big as possible, because bigger it is, more generalized answer I will get, right? Let's say I told you 2 plus 2 is 4, 3 plus 9 is 12. And let's say I give you a lot of example, and then I just ask you one question: what is 5 plus 5? You said 10. I cannot say you are a very brilliant student, right? Maybe I need to test you on at least 5-6 different examples. You got my point? That
Okay.
one answer you could have given by chance as well. Right? So if I want to be very sure on your intelligence, then what I need to do? I need to ask you multiple questions. And the more the number of questions that I will ask you, right, the more confident I will become that you are, let's say, smart. Right? So I want my test data to be as big as possible. But the problem is, more that the bigger you're gonna make your test data, lesser your training data will become.
Okay.
Right? Because I have limited number of questions. So I can ask you a lot of unseen question, but that means that my training data will reduce. Right? Let's say now if I have 10 questions, I'm keeping, let's say 9 questions to test you, but only 1 question to kind of train you. Right?
Okay.
In that case also, you will not be able to learn anything. Okay. Any other question, anyone?
Like how would we interpret the results, if we get the same results, okay, from 80-20 and 70-30. So how do we interpret those results then? Like both.
It can happen. You're saying that you're getting the same result for 80-20 and 70-30, right?
Yes.
Yeah, it can happen. Yeah.
Okay. I mean, how do we interpret it? Like, how do we say that in?
See, modeling is a very iterative process. Okay.
Okay.
That's why I was saying that the things that I'm telling you is a very generic things. These are not rules. So when I say it is a very iterative process, it means that yes, it can happen that 70% training data and 30% test data might give you a better accuracy as compared to 80-20.
Okay.
Right?
Okay.
This can also happen that maybe 80-20 will give you a little better accuracy as compared to 70-30. And this can also happen that maybe 80-20 and 70-30 might give you both might give you the same results. Right? So
Okay.
all the possibilities are there. Which one is better, to be very frank, we don't know. Right? So it's just that we know that we should not keep training data too less, at the same time too high either. So in general, people keep it as 80-20. But will it, if I will keep it 70-30, will it make a very drastic difference? No. Okay. So it's not like in one case you are getting model accuracy as 85%, in another case you are getting it as 75%, just because you change the ratio. That will not happen.
Okay. Okay.
Okay. But which one will give me a better result? No one knows in advance. And what if 70-30 is giving me a better result than 80-20? What does that tells me? We don't know.
Yeah, what I meant to say is like if we know the accuracy, okay, after splitting the training and test data. Okay, so I just wanted to know like how do we interpret it? If both are giving the same accuracy, test accuracy, how do we say that in layman terms?
It's the layman terms only that okay, so it's a layman terms only that this one is giving me a better result as compared to the other one. See, the people don't care how you got to the answer. Okay.
Okay.
All we care is that what is your model accuracy is, right? What you have done, what all iterations you have done to reach there, that does not matter. Okay. And there is no fixed way of doing it. They are just directions. Okay. For example, 80-20 is a direction, but no one can guarantee you that this is the best ratio which is possible. Okay.
Okay.
Cool. Let's move to the next part.
One question. So if model complexity increases at the overfit rate, why the test data is decreasing?
Why the test accuracy is increasing?
It's the test data is test, right? It is going down, right?
Right. Test accuracy is going down. Yes.
Yeah. Why variables are increasing, so test is decreasing?
Right. So what starts happening is, take it as this thing. There is this concept that see, each variable is a new dimension. Okay. Imagine it like this. I will try to explain as much as I can. Just imagine this. Let's say I have multiple data points. Right? Let's say I have two variables, variable 1 and variable 2. Now, if I will hypothetically just imagine if there was only one variable, that is variable 2. Only one variable was there instead of two variables, then how these points will look like? This point will be here, another point will be here, here. You will see that all of these points will be very, very close to each other. You agree?
Yes.
So when I have lesser number of variables, the points are more close to each other, right? When I have more number of variables, the distance between the points increase. Is that part clear?
Yeah.
Right? Now what starts happening is, to generalize anything, right? To generalize that anything, I need at least some number of data points at a place. You agree?
Yes.
Right? I need at least some number of data points. Let's say, for example, if you have seen only one person in your life who has done PhD and he is earning, let's say, 2 lakh rupees, can you make a generalized statement that everyone who has done, who will do PhD will earn 2 lakh rupees per month? No, right?
No.
Right. Similarly, let's say there is a guy who has done PhD and he is not doing anything. He's just sitting idle at home. So let's say there is only one person you know who has done PhD. Can you say that doing PhD is the wrong thing? Again, no. Right. To make a generic comment, we should have enough number of data points at a given place. Right. So it means that if I want to comment about what is people earn after PhD, it means that at least I should know 20, 30 different people who have done PhD, so that I can say that, okay, on an average after doing the PhD, this is how much you can expect. Right? Similarly, let's say if you have seen only one tiger in your life and that tiger weighs, let's say, 120 kg. Does that mean that all the tigers almost weight 120 kg? We don't know, right? We need to have at least 30, 40 tigers. We need to weigh them, and then we will know what is the average weight in general of a tiger, right? Only then, let's say, if in the future, if I'll ask you, okay, there is a random tiger in the Bangalore Zoo, what do you think is the weight of that tiger? What you will do? You will make a educated guess about it. Point being is that I can only generalize when I have enough number of data points at a place in a particular area. As we start adding more and more number of variables, the variables are also called dimensions. Okay, variables are also called dimension. There is a reason behind why variables are called dimension, because it adds a dimension. V2, I had only one dimension. This was 1D, one dimension. When I added one more variable, it became 2D, two dimensions. When I will add one more variable, V3, it will become 3D, three dimensions. So if you have 10 variables, that is actually a 10D data. Okay, 10 dimensions are there. And more the number of dimensions you add, the points go even more far and more far away from each other. Okay, so what starts happening? Whenever you are trying to look at a point, you will not be able to find any other point closer to it. Okay, so you will not be able to make a generic comment, right? Because whenever you are looking at a point, is there any other point around that point? The answer is no. Like, is that, imagine it like this. Imagine it like this. Let's say I have a lot of green points. And I have a lot of red points. Now, if there is a new point, you don't know the color of it. Let's say that point is here. You don't know what is, the color of this particular point. And I'm asking you to make a prediction. What will be your prediction, whether it is green or red?
It's green.
It's green. This one. This is the red, bro. No?
Yeah, red.
Right, because it is more close to the red points. Like all the points that you see around this particular point, all the points that you see around this particular points are red points. And that's why I can say that most probably this particular point is a red point, right? How I'm being able to make that comment? By looking at the points around this particular point. Because a lot of red points are closer to this one, I can say that this point is also going to be red. So, but when you increase the dimensions, the point starts going further and further away from each other, right? And when you take a point, an unknown point, and you try to see that, okay, what does this point look like? Does it look like red? Does it look like green? Does it look like yellow? By looking at the other points around it, you will not be able to find any other point around it. Okay, that's where the model start giving you the wrong results. That's why when we add more number of dimension, the points go further and further away from each other, and we have lesser and lesser points in a given area. When we have a very less point in a given area, okay, then your model starts to overfit, because now the model is not being able to generalize, right? This, I will go back to the same example of student and teacher. If I will give only two examples to you, that 2 plus 2 is 4, and let's say 3 plus 9 is 12. And if I'll ask you what is 10 plus 12, you will not be able to answer it. The reason being is you were not able to generalize addition in your mind, because I had given you very less data, only two addition example. So as you add more number of dimensions, the points go very far away from each other, and it becomes very difficult for model to generalize anything. So what model starts doing? The model starts mugging up everything, right? That I cannot understand what is happening because I'm not being able to generalize it. So I will start remembering it. Okay. Is it a little bit clear now?
Yeah, thank you.
Okay. In machine learning, it is called curse of dimensionality, right? The meaning being is nothing but as you add more dimensions, the points go more further away from each other, and that makes it harder for the model to generalize anything. The short form is curse of dimensionality in case of machine learning. Okay, I hope you guys were able to follow any question, at least at some level. You guys were able to imagine what I was trying to say.
Yeah.
Okay, cool. Now, what we will do is we will quickly try to refresh a few concepts of mathematics. Like first thing is, what is your integration? What is differentiation? Can anyone tell me what is integration and what is differentiation?
Integration is area under the curve.
Right. And what is differentiation?
Slope of
Mm-hmm.
a graph.
Very nice. Very nice. Right. Oh, I started writing Apurva only. It area under the curve. Area under the curve. And this is nothing but slope of curve. Okay. What do we mean by that? Let's say if I have a data set, if between any 2 points, okay. So let's say I have a curve like this. Okay. Now, if anyone will ask me that, okay, Puneet, can you calculate what is the area under the curve between this x1 and this x2? Now, if someone will ask me what is the area under the curve between x1 and x2, how can we calculate it? Using integration. So for any given curve, if someone will ask you what is the area under the curve between, let's say, point 1 and point 2, that can be done using integration. How differentiation works is, differentiation tells you that, okay, for any given point, let's say I gave you this particular point, x3. For any given point, what is the slope of the curve? Right? This is the slope of the curve, and this is your area. Okay, so if you want to know what is the slope of the curve at any given point, I will be using differentiation. Whenever I want to know what is the area under the curve at any given point, we will use integration. Okay, now we will just do a few quick things. The first thing that we need to remember is differentiation of x with respect to x is nothing but 1. Okay, differentiation of x with respect to x is nothing but 1. How can we remember this? Let's say if I have an equation y is equal to 3x plus 9. Okay, what is the slope of this particular curve?
Y is equal to mx plus 3.
3, 3.
The slope of the curve is 3.
3.
And what is 9?
Constant.
Constant or intercept, right?
Yeah.
So it is more or less like this. Okay. Right? When x is equal to 0, y is equal to 9. Okay. Okay, I need to extend it on the other side. Okay. When y is equal to 0, x is equal to 9. Sorry, x is equal to 0, y is equal to 9, maybe somewhere here. And when y is equal to 0, x is equal to
-3.
-3, right? So let's say somewhere, maybe here. Okay. Then this will be our line. Okay, it was not as straight as I was planning to make it. Okay, so this is our line, and the slope of the line is equal to 3, right? So how we will solve it? When I say that differentiation of x with respect to x is equal to 1, now let's use that to calculate the slope of this curve. Because why we use differentiation? To find slope of anything. So we'll say differentiation of y with respect to x, which is in this case differentiation of 3x plus 9 with respect to x, right? Which is nothing but differentiation of 3x with respect to x plus differentiation of 9 with respect to x. Differentiation of 3x will become this. Differentiation of a constant is always 0, right? Because a constant does not vary. Okay, does not change. So differentiation of that will be 0. What is differentiation of x with respect to x?
1.
1. So the answer is going to be 3. Okay. So from here, there comes the concept of the differentiation of x with respect to x is nothing but 1. Okay. Just 1 minute. 100. Okay, now let's learn the second concept. Differentiation of x square. Guys, can we do one thing?